We're starting section 4.3, the mean value theorem. This includes the Rolle's theorem and the mean value theorem, and then the first derivative test, because first derivative test actually is a result of the mean value theorem. Rolle's theorem. Suppose that f is a function such that f is continuous on a closed interval a and b, and f is differentiable on open interval a and b, and f of a is equal to f of b. Then there exists a value c in between a and b such that f prime of c is equal to 0. So in here, we can see the picture. The picture shows at A and at B, the y values are the same, and then you see that there's a C in between them, and that where you see a horizontal tangent line, which means that the derivative at that point is equal to 0. Okay, so another way of rewording Rolle's theorem is that with all these hypotheses satisfied, f being continuous on a closed interval, f being differentiable on an open interval, and the two values at the endpoints to be the same, we can say that then the secant line, here's the secant line going from, secant line is down in the bottom, between a and f of a and b and f of b is parallel to the tangent line at some point in between a and b. And so the reason we worded this, the Rolle's theorem again, suppose that f is a function such that f is continuous on a and b closed interval, f is differentiable on a and b open interval, and f of a is equal to f of b. Then there exists a value c such that in a and b such that f prime of c is equal to 0. So what happens if f of a is not equal to f of b? If we change the Rolle's theorem to get f of a not equal to f of b, so would this still, the statement that we said before, would that work? So the tangent line at the point, there would be a c between a and b such that the tangent line at c is parallel to the secant line from a and f of a and b and f of b. Is this possible? It turns out yes, and it turns out that it can be proven using the Rolle's theorem, and that's called mean value theorem. So what is mean value theorem? Suppose that f is a function that is 1, continuous on closed interval a and b, and 2, differentiable on open interval a and b. Then there exists a value c in a and b such that f prime of c is equal to the average rate of change between a and b, which is f of a minus f of b, f of b minus f of a over b minus a, or f of a minus f of b over a minus b. Now, notice again, this part is the slope of the secant line, this one is the slope of the tangent line. So we're saying that the secant line between the 2 points is parallel to the tangent line. So here's a few pictures of them. Let's say a function is continuous between a and b and differentiable, and here also, and then I draw the secant line between the two endpoints, and then is there a point that I can find? See, now I'm trying to do the picture on the left. If I go parallel, 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 basically I end up at some point at the very end that the parallel line only touches the graph. Now, the right hand one, if I go parallel, 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 I end up with 2 points that are that have tangent line parallel to the secant line between the two endpoints. So this sliding is it gives you some idea about how the proof actually goes for the theorems, but and also it gives you how it works. And so again, there could be multiple value C's such that the tangent line at those values are parallel to the secant line, and at least there is one, and if the theorem is satisfied. Now, look at this example. Look at f of x equal to x to the third minus x on the interval 0 and 2. So the requirements of mean value theorem are all satisfied. The function is a polynomial, is both differentiable and hence continuous, or we can say continuous, and we know more, they're differentiable everywhere. The slope of the secant line between the two endpoints is f of 2 minus f of 0 over 2 minus 0. F of 2 is 8 minus 2, which is 6. F of 0 is 0. 6 divided by 2 makes 3. Is there any place in between that we have? And so this question is telling me that there is a point in between. So there is a C between 0 and 2 such that x to the third and the derivative of the function, which is f prime of x equal to 3x squared minus 1, is actually can take the value 3. That is f prime at c is equal to 3c squared minus 1 should be equal to 3. So mean value theorem tells me that, but then I can solve this question. I can solve the C and find the value, which is going to be 4 and square root of 4/3, which is approximately 1.155, right? If you solve, you get that value. And so at that point, at c equal to that value, the slope of the tangent line is equal to the slope of the secant line between the two end value. So mean value theorem guarantees, but then we can also solve and see what the value is. So in example 1, we saw that mean value theorem guaranteed that the slope of the tangent line is the same as the slope of the secant line of the two endpoints at some point. And now we could also solve that point and find it. Now look at this problem. If I'm looking at this problem, it again satisfies the mean value theorem. And so I want to know if over here I can find this C also or not. So again, polynomial, continuous, differentiable. The secant line, again, if I plug in 0 and 6 and 2, I get 0 and 6 respectively, and then the slope of the secant line is going to be 3. And then this guarantees by mean value theorem that there is a C in 0 and 2 such that f prime of C is equal to 3. Can I solve for that C? Let's take the derivative. The derivative is going to be 4x to the third minus 2x minus 3, and I plug in C and I set it equal to 0. And I get a polynomial of degree 3. And polynomial of degree 3, even though there is an equation, then we can use that to solve it. That equation is too complicated to be used. So unless we can factor them, we don't really solve these equations. polynomial of degree higher, there's not even any pattern that we can solve for the roots. But polynomial of degree 3s are the polynomials that have a method not quite as simple as quadratic polynomials. So we kind of can assume that this finding the solution is at least difficult for us without a numeric method. And so, but we know that the solution exists, and that's the solution that we see.